This week, we shall extend our discussion on isolated converters. We have studied till now the forward converter and the flyback converter in the isolated class. The forward converter is derived from the buck converter, and the flyback converter, as you know, has been derived from the buck boost converter. The forward converter has few more derived forms. The push-pull topology, the half-bridge topology, and the forward topology. These three topologies we will look at the initial stages of the lectures and see what are their advantages and where they will be used. Generally, you will see that these three topologies will lead to more compact transformers because they utilize the flux swing much better. In the forward and the flyback, you saw that the flux swing was always from 0 to 5M. But in the case of the push-pull, half-bridge and the full-bridge topologies, the flux swing will be from minus 5M to plus 5M, and therefore the transformer core is better utilized, and therefore for a given power the size will be smaller. The full bridge topology, which is the one which would lead to the most compact form and the most popular, especially at the higher wattage levels, will also be looked at. Then after that, we will study a bit on the multiple output converters. Actually, it will be the same forward and the flyback topologies with multiple secondary windings. And when you have multiple secondary windings, how will you get regulation from all the outputs? So before that, we should also know how to do closed looping of a particular output. So we shall briefly study the closed looping aspect of the converters, and then later extend our discussion to multiple outputs and see how they will get regulated. And then if time permits, we can look at some advanced control aspects. So this is in essence a summary of what will be covered in this week's course.
You see that this circuit is that of a forward converter. You recognize that this is the forward converter and this is the demagnetizing winding. Now I'm going to describe the evolution of the push-pull converter using the forward converter. So first step, let us look at the primary side. We have the demagnetizing winding. The main function of the demagnetizing winding is when the switch is off, the energy in the core is put through the demagnetizing winding into the supply. Now let us enhance that concept a bit further. During the time when this primary winding is off, instead of putting the energy into the supply, let us put the energy into the output. So that is the concept which will come in the push-pull. So instead of calling this as a demagnetizing winding, we will be calling it as another alternate primary which will put into the output instead of putting into the input. So how is this going to come about? So we shall use the same winding. We will call it as another primary. These two are having the same turns ratio. So I will put this, I will flip this and put this winding on top above here like this. Now let us move this whole converter a bit down so that we have some space up there, and then I will move it a bit to the right side so we make up some space. Next I will clear up some clutter here and now connect this. Now this portion, this diode portion is actually connected here, and instead of connecting a diode, I will connect one more switch in the place of the diode to this as follows. So I will connect this transistor like this at this point. this end you already have the transistor. I don't want this diode because instead of this diode which is connected here, I have connected the transistor there. This ground can come up here, and remove this conductor piece and remove this, and let me switch over and flip this up like this, and then I will connect this transistor here, and we have something like this. Now this is a push-pull circuit. So what I will do, I will move this down and extend these two here to indicate that is coupled. This is not needed, and this would be the push-pull as far as the primary side is concerned. So in this primary portion, you will see that we will name this BJT as Q1. It has a drive VG1, and then you have Q2 which has a drive VG2, and VG1 and VG2 are never applied simultaneously. They are mutually exclusive. Now to understand the circuit better, we should know that when Q1 is on, this winding, this primary winding is the one which is in action. So let me give it a different color. So when this winding is action, this dot polarity, this is the secondary winding that is in action. So let us mark that also in blue color, so that it is easy for you to understand that when Q1 is on, this blue winding is in action. Accordingly, the blue secondary winding is also in action, which delivers the energy to the inductance and the output buck circuit in a way which we are familiar with. When the transistor Q1 is off, this blue winding is out of the picture, but there is energy stored in the core of the transformer. So we would have expected that in the absence of Q2, we had earlier put a diode, and the diode will allow the freewheeling to happen through the Vin. Now what we expect to, we will let us say for now that there is no change in the flux. We will energize the core in the opposite direction by turning on Q2, which will, because the dot polarity is now towards the switch. Here the dot polarity is away from the switch, it is in another polarity, and when you energize this switch, it is trying to make the magnetizing current flow into the non-dot end and out of the dot end. When Q1 is on, magnetizing is flowing into the dot end, out of the non-dot end. So when Q2 is on, magnetizing current flow into the non-dot end and out of the dot end. So this will try to pull the core to 0 and go past 0 into the negative region. And during that time, when this is off, we would want this to supply energy to the output rather than to the input. So let me mark this one in another color, and let us say this is this. And to handle that, we need one more winding at the secondary side, which will have a similar kind of dot polarity to pump into the output. So what we shall do is try to make the following changes. I will make these changes and then explain to you. So now you see that I have made for this primary an appropriate secondary with an appropriate dot polarity, and they are connected in the secondary like this. So this should also charge up this. So what we will do, we will connect the diode in this fashion. I'll connect the diode like this. Should understand this, this is not a junction point, the diode is flowing in this fashion. And let me probably give a different color for this diode, so that to indicate that this is the path flow for this. Let me also change the appropriately. Then this would be the other, like this. So now it becomes much more clearer. So you see that you have two possible circuits to charge the inductor. Let me explain that to you in a moment. So you see here, when Q1 is on, the dot end is positive. All the dot ends are positive. So the blue dot end is the only coil portion of the coil which can pump energy into the inductance in this fashion. There is no other circuit which can do that, which can possibly pump energy during that time. Let us consider the green portion of the circuit. Dot end is positive. There cannot be a flow of current in this fashion. So this is out of the picture. This is reverse bias, and because the dot end here is positive, this is positive and this is reverse bias. So therefore the only possibility of energy flow is through the blue and through this blue circuit into the output capacitors and R0. Now when the switch Q1 is off, let us say for some time both Q1 and Q2 are off. During that time there will be a freewheeling of the inductor, and it will freewheel through this, or it could also freewheel in this path as we are seeing. And then after some time, let us say we are switching on Q2. The moment you switch on Q2, the dot end is connected to the ground and the non-dot end is connected to the positive. So the non-dot end is positive, which means the non-dot ends are positive. In this case, the green, the non-dot end, which is this green, has capability to pump energy into the inductor in this fashion. Follow the arrow in which I am moving this arrow, so that will give an indication of the current flow through the circuit during the time when Q2 is on. So in this way you see that whether Q1 is on or Q2 is on, there is energy pumped into the inductor, the magnetizing circuit. So the inductor energy increases, and then during the time when both Q2 and Q1 are off, the inductor is freewheeling both through the green path and the blue path. So this is how the push-pull converter will operate. Recognize here this output segment is essentially a buck converter. There are two paths basically happening basically due to the two primaries and the two secondaries with common buck converter output. So this is called push and pull, basically because of the circuit topology. When Q1 is on, the flux is pushed to one side, and when Q2 is on, the flux is pushed to the other side. So this is the push-pull circuit operation. So you see that this is the push-pull converter that we have discussed. We will get a bit more insight if we look at the waveforms. Now to do the waveforms, I have here a template of writing the waveforms. Now this first line here indicates the drive that we are giving to the two switches Q1 and Q2. VG1 comma 2 is what I've indicated, means both VG1 and VG2 are given on the same timeline. Right now I will not discuss explain this for the moment, just leave it at this. What is this DTS and 1 minus DTS, I will explain it later. For now, the important point for you to focus on is that Q1 is on during this period. Then there is a period of time where neither Q1 nor Q2 is on. In this period of time where I am showing this arrow, both Q1 and Q2 are off. Then during this time, I said that Q1 and Q2 should be on mutually exclusively. Q2 is on and Q1 is off. And again, you have a period of time when both are off. And then Q1 again is on, both are off, Q2 is on. So in this fashion, you have alternately Q1, Q2, Q1, Q2 being on, and in between there is a period of time when both are off. So this is the pattern in which we will give the gate drive for VG1 and VG2, and accordingly Q1 and Q2 will switch. Now given this pattern, let us see how the waveforms will appear at the VP, the pole, and then of course the inductor currents. So considering the discussion that we had earlier, when Q1 is on, we see that the blue portion of the circuit is active. So when Q1 is on, the dot side is positive. This dot with respect to the ground is Vin, and this dot with respect to the center point, midpoint, would be N times Vin if we have a turns ratio of 1:1. This is 1:1. These two are same, and these two are also same, and on the secondary side it is N times turns ratio. So here we are having N times Vin, and which appears at VP. So at VP you will have N times V in here, and that will charge up the inductor, and we will indicate that portion of the waveform in blue here. So let me indicate that. So as a blue waveform, so whenever Q1 is on, you will have this kind of a thing. Here Q2 is on, and again Q1 is on here. So let me indicate this. Now this is what will appear at which point? It will appear at VP, the pole voltage point. And then when Q2 is on, the green portion is active, and you will see pole voltage will get the same V in during this time. So during the time when Q1 is on, I am going to write here N times V in will appear here. And during the time when green portion is active, Q2 is on, you will get N times V in here. But remember that this will be plus with respect to the dot here. In the case of the blue, this would have been plus with respect to this, maintaining the dot polarity convention. So if you look at this wave shape here, look at this wave shape. So you are having at that VP a blue portion which is high, then a low, then again a high and the low. Now if you take the switching frequency of Q1, Q1 is switched here, then nothing up to this point. Here you have the switching of Q1, and take the pole voltage frequency. For the switching frequency of Q1 or Q2, the frequency that appears at the pole voltage is double because of the ORing effect of the green and the blue portions of the circuits. Because of the ORing effect, at the pole voltage there is a doubling of the frequency, and therefore we now define this dTs and 1 minus dTs with respect to the pole voltage wave shape. So the pole voltage waveform, if you take from this point to this point, will be considered as Ts. Then the portion when it is high is considered as dTs, and the portion when it is low is considered as 1 minus dTs. Now that is what I have indicated here. The portion for which either Q2 or Q1 is on is called dTs, and the portion when neither of them is on is called 1 minus dTs. So this buck converter operation is based on this kind of a definition, and we can use this kind of a definition to find the V0. So now what would be V0? V0 would be the average value of this. So let me now draw the average value. So average value of Vp will be V0. And I know that the high time is dTs and the low time is 1 minus dTs, and the average is given by n times Vn into d. Now this is n times Vn. Now d as defined here, where the Ts is one period of the pole voltage. Ts is defined with respect to pole voltage Vp. That is important because the switching frequency is half the pole voltage frequency. The inductor will be designed at a frequency which is double the switching frequency of Q1 and Q2, because the inductor is because of the ORing effect, inductor is saying double the frequency. This is a very key point which you have to note in all the three topologies, which is the push-pull converter, the half-bridge converter and the full-bridge converter, where in all these three converters the output side or the secondary side is exactly like this, exactly similar. Only the primary side will change in the half-bridge and the full-bridge converters. So the inductor will see an ORed effect of the two components, and therefore the frequency of the voltage across the inductor will be double the switching frequency on the primary side. So that is one aspect which you have to consider, and the D is always defined with respect to the pole voltage. This is the important aspect in the case of this push-pull, half-bridge and full-bridge topologies. Let us look at the current through the inductor, IL. So during the time when Q1 is on, we see that the blue portion of the circuit is active, and at the pole you have NVin. So NVin minus V0 by L will be the rate at which the current will increase in the inductor. So this rate is NVin minus V0 here, we know it is V0 by L. So that is the rate at which it will increase. Then it will come back during the time when the inductor is freewheeling, during the time when both Q1 and Q0 or Q1 and Q2 are off. Then again Q2 is on, the green portion of the circuit is active, and Vin is applied at the pole Vp, and it will again rise up with the rate of Vin minus V0 by L. Then it will fall down, and when it is falling down, it is at V0 by L rate, and this keeps happening every cycle. So this is how the inductor current will look like, and the average of that is I naught. So all these are just like the buck converter, because the output portion of the circuit is exactly like the buck converter. Now if you look at the rating for Q1 or Q2, see the VCE or rating for either Q1 or Q2 should be at least greater than 2 times Vin. How does this come about? So you see here, when Q1 is on, this is Vin, dot is positive Vin, and the non-dot end is connected to the ground. Now assume Q1 now switches off. The moment Q1 switches off, there is a reversal of polarity. This will be having plus, and here it is minus Vin, and there is a Vin here connected in the circuit. So you are having Vin and another Vin due to the reversal of the polarity appearing across Q1. So Q1 should withstand at least 2 times Vin. Likewise, when Q2 goes off, when Q1 is on, let us say, dot end is positive Vin, this is Vin plus this Vin. So in this portion of the circuit, you will see that Q2 has to withstand 2 times Vin. So the rating for Q2 and Q1 is as written down here. Likewise, the diode, when let us say this diode is conducting, this diode is off, one end of the diode is at NVin, and the other end of the diode here, if you see, during the time when this is conducting, is having another NVin. So this NVin plus this NVin, this conducting diode is coming across this. So the diode overall should be capable of withstanding 2 times NVin. So that would be the rating of this. Deciding the ratings of the inductance and C is exactly same as we had discussed in the buck converter circuit. Now there is one small aspect which I want to discuss, that is the freewheeling aspect and the flux within the core. Then the discussion on the push-pull will be more complete. Let us look at that. Now consider the flux waveform. Now the flux waveform within the core. Now let us say the flux in the steady state, it at the point of starting, it is at one side of the core. Let us say it is at minus phi m, and during the time when Q1 is on, there is magnetizing current which is flowing through, and it is magnetizing the core from minus phi m to plus phi m. So let us say this is plus phi m. And then during the time when both Q1 and Q2 are off, so when both Q1 and Q2 are off, the inductor current goes in this fashion. At this point, it equally divides in this way and in this way. So the inductor current IL will divide into IL by 2 on this side, IL by 2 in this side, they come join and then again become IL. And so if you look at the magnetics, there is an IL by 2 entering the non-dot end, coming out to the dot end and moves in this way. There is an IL by 2 entering the dot end here, coming out of the non-dot end, and then joining up and here, joining up at this VP point, pole point, and then going as IL into the inductor. So you see that in the secondary of the coil, there is an IL by 2 entering the non-dot end, there is an IL by 2 entering the dot end. So N into IL by 2 is the MMF which is generated inside in the core, and on one side it is in one direction, and due to this current flowing in the other coil in another direction, they will cancel each other out, and effectively there will not be any voltage here, the flux will not change. d phi by dt will be 0 because of the cancellation effect of the equal currents flowing through these in opposite magnetic sets. So therefore, once there is no change in flux, there is no d phi by dt, voltage is 0, d phi by dt is 0, flux continues to be wherever it was. And then again there is a dissymmetry, Q2 is turned on, and now in an opposite sense magnetizing current is flowing, and this will go down up to minus phi m from plus phi m. And at the other end, when the both Q1 and Q2 are off, again the inductor current is freewheeling in such a manner that the current flows in an opposite sense in both the windings. There is no change in the flux, and the whole operation keeps continuing. So this is how you would look if there is a possibility or a chance to look at flux. This is how it would look like within the core of the push-pull converter, and this would give you some insight when you are making the push-pull transformer along similar lines which you did for the forward converter. Now I would like to see the currents that are flowing through this diode and this diode. So these two currents are actually the ones that are flowing through the inductor. They are basically the inductor current during the time when this particular diode is on, or the inductor current during the time when this particular diode is on. So during the Q1 period, inductor current and this blue diode will be the same. During the time Q2 period, inductor current and the green diode will be having the same current. During the period when Q1 and Q2 are off, inductor current will equally divide between the two diode currents. So using that principle, we can write the diode currents. So let me now go about drawing the diode currents. So first let me take the diode current D1. I will call this one as D1. So ID1. So during the time when Q1 is on, the diode D1 will be conducting. So it will take the same wave shape as the inductor current. Then the inductor current will actually, I'm now going to put it dotted, will go in this shape. And then during the time when Q2 is conducting, actually the ID1 current will not be flowing. So I can safely say that it will be 0 during this time. And again during the time when Q1 and Q2 are off, there will be some sharing of the current which we will come to. And then again when Q1 is on, it will take the shape and continue. Now I showed the dotted because that is not the way, that is not the profile of the current flowing through the diode. Now when both Q1 and Q2 are off, it is half of this falling current which will flow through ID1, the other half will flow through ID2. So let us say half of that is this, and the remaining half I will say equal, which will flow through ID2, if this is D2. So and likewise at this point also it. So the diode current will look something like this. It goes, and during the time when Q2 is on, you see that the current goes like this, and half of it only will flow through this, other half will flow through, sorry, the other half will flow through the D1 diode. So half and half will be shared during the time when both are off. So you will see on the scope a pattern of the diode current which is like this, and likewise for the other diode too. You will see the pattern of the diode current which flows in this fashion. And jumps up and then goes like that. So this is how the diode currents will flow, and this is what you would actually see. Let me remove this dotted portion, and this is what you would actually see on a scope for the diode currents. So this is how the push-pull converter will operate. Now you will see that it is very easy to understand the half bridge and the full bridge. The secondary part, the whole of the secondary part is exactly same. There will not be any change in the secondary part of the converter, whether it is push-pull, half bridge or full bridge. The operation is also exactly same. These diode currents will be exactly same, and the input-output relationship, the inductor currents and the voltage across the inductors, the frequency with which the DTS and 1 by DTS that we say, the pole voltages will be very, very similar. What will change is the primary part, and that is what I am going to change and then point out the difference to you, and this will give you an idea of how the half bridge and the full bridge circuits will work.